Let's begin. Put your names up, please. Last lecture of the week, for me at least. Canvas is down. There will be one data file we will use, but I put it on Google Drive, and I'll share the short URL with you on the slides, so we have all the information we need. And this would probably be a short class as we finish numerical descriptions of data. Hopefully we can do it on time. I want to continue where we left off last time. Variance, just give you a very quick reminder of what we were trying to measure. With variance, with numerical descriptions of data, we started asking, what is the center of the data? First, we looked at mean, median, and mode. We realized that the median is not affected by outliers, but the mean is heavily affected by outliers. Think of the salary example. One salary that's 100 times the average, the rest of the salaries could skew the mean significantly high, but it does not affect the median. And we saw how that looks on distributions, symmetric, left and right skewed distributions. The next description of data to try to interpret it and understand it is called the spread or dispersion of the data. And the quantity that measures the spread of the data is called the variance. And we always choose, this was an important point to make. If you remember last time, I said the average is always our gold standard, not the median, interestingly, but the average is our gold standard to measure things relative to. So we are measuring spread of data relative to what? Relative to the mean. We're going to measure the spread of the data relative to the mean. And the quantity we looked at was, if we take say the data is distributed around the mean that way, and if we take the distance of each data point, so these x values or the numerical values in your data could indicate salaries, could indicate temperature, radon concentration, and so on. If you take the difference of each data point with the average value, then you're going to get a bunch of distances, an array of distances from the mean value. And then we thought if we can average all of those distances, that gives us a sense of how much the data is spread around the mean. That's very important. It's spread. It needs a relative point where we measure spread. Then we realized that this measure is bad because they just cancel out. Things on the left side of the average could be positive or negative depending on whether you do x minus x bar. And then the opposite is true, and then they end up all canceling out, as we showed here in this formula. And then we said, okay, maybe we take the absolute value, but the absolute value has issues. It's discontinuous at 0 and whatnot. And then the last argument was to think of these distances as the elements of a vector. And how do you measure the length of a vector? You take the Pythagorean norm. Right? You sum the length of a vector squared is the sum of its components squared. So if you think of the total distance from the data point to the mean as these are the components of that distance, then taking the sum of their squares is going to be the total distance. Now, we need to average it because this is not really a vector. This is on average, how far are the data scattered around the mean value. And we divide by the number of points. Specifically, we need to divide by n minus 1. I'm going to come back to that point later. But if you told me n, that's not an issue. But moving forward, you need to distinguish whether you need to put n minus 1 or n. We will not understand this until several lectures further down. And even then, it might still be a little fuzzy because there's some math involved. Now, take this value as the measure, we call that the variance, and for a sample we call that s squared, and it's a much better approach, much better measure than taking the absolute values because they're non-differentiable at 0, they're discontinuous. This variance has certain properties when we develop the full continuous theory of probability distributions and how that ties into statistics. Now, in general, we can do this for a sample and we can do it for a population. For a population, we call this sigma squared, and the mean for the population is designated by mu. Remember, we distinguish between sample and population. And the formula is the same. You're taking the distances from the mean, x minus mu squared. Remember, summations are carried over all data points. When I'm not indicating subscript or superscript, this is summation over all the data points. So going from 1 to capital N. Now notice the denominator for the population variance is n, not n minus 1. But the sample variance is the formula based on the sample mean, which is x bar, but the denominator is n minus 1. Okay? Now compare that to the measures of the mean value, where the mean of the population was sum of all data points over n, capital N, the total number of subjects in the population. But so is the sample mean, is the sum of all points over small n, right? For the variance, it's different, okay? I'll try to explain why n minus 1 in a very hand-wavy way in a second, but it's not going to be satisfying, and I understand that. It wasn't never satisfying to me until I got to continuous probability distribution. Historically, people put n in the denominator, okay, when they first were measuring, because they just took the average, sum of the square distances divided by the total number of points, whether sample or population. That's an arithmetic average. But then later, a correction was introduced, and then later, full probability theory, continuous probability theory, demonstrated that, yeah, you need an n minus 1 in the denominator. So I'll give you the hand-wavy explanation, and then I'll explain a little bit the more rigorous explanation, which we will hopefully get to later. It will be a homework assignment. Okay, so why do we have n minus 1 in the denominator? The common explanation, which I think is not satisfying, but I will say it anyway, is that has to do with what's called degrees of freedom. A degree of freedom is an independent piece that you can change to fix something. So, you know, like the knobs on your car, you can change volume, you can change, frequency, but there are some things where if you change one, it's going to change the other. They're dependent on each other. So then you can't count those as two separate degrees of freedom. They are dependent on each other. When you look at a sample, the mean of the sample depends on the sample. It will change if you change the sample. But a population, the mean is fixed. It's not dependent on the population is the population. There's no other population. It's just everyone, all subjects in whatever you're measuring. So in that sense, like I said earlier one time, I said the mean is a property of the population, not something you compute. Although, yeah, we compute it by adding the values and dividing by n. But really, it is a property of the population. It doesn't change in the population. It's fixed. But the sample, the mean, is going to change from one sample to another. Why? Because the sample mean is computed from the subjects in the sample. And then you ask yourself, well, if I know n people in the sample, n subjects in the sample, I can compute the mean. But if I know n minus 1 subjects and I know the mean of the sample, I can compute the last point in one and only one way. So that means I really only have n minus 1 degrees of freedom because I already used the mean in my calculation. If x bar was not in the calculation, then I would have a total of n degrees of freedom. Just like when we computed the mean of the sample. We only used all the xi, so we divided by n. But in the computation of the sample standard deviation, we're already using the mean in the calculation. So we took the mean as if it's a quantity we know. What are we left with? Not n degrees of freedom or n subjects. We're really left with n minus 1. Why? Because n minus 1 subjects plus the mean is going to give us the value of the last subject. That's the kind of explanation you'll find on YouTube, on the internet. It's not very rigorous, but it is somewhat, that's the most intuitive we can explain. And this kind of clarifies here that the population variance is based on the actual population mean, but the sample variance is based on the on different samples. And so once you use the mean, you've already took out 1 degree of freedom. If you look at my, anyway, when we talk about regression, I'll explain that as well. Anyway, now the more rigorous proof, which we will come to later, is that once we get to statistical inference, if you remember, the idea was we want to infer properties of the population, mu and sigma, from statistics of the sample, x bar and s. And we want to compute x bar and s so that we want to design them in a way such that if we sample infinitely many samples, if we took all the possible samples we can sample, we can actually get the exact mean value of the population, mu, and the exact standard deviation, sigma, of the population. Okay? Now, that means you have to compute your mean value of the sample and your sample standard deviation in a way such that in that limit, you'll get the true value. How can you prove that? There's some math that you can do through what we call the expected value of an estimator. What's an estimator? It's simply that formula we used. S squared, in this formula, we call that an estimator of the population standard deviation. This particular formula we call an unbiased estimator because in the limit, as the number of samples goes to infinity, we get the true population standard deviation. If you were to put n in the denominator, you can prove that in the limit of infinitely many samples, you're not going to get sigma. You're going to get something else times sigma squared. Okay, so you're not getting the true estimate of the population standard deviation, and we call that a biased estimator. You can have biased and unbiased estimators. That's fine. They're an approximation to something, but as long as you understand what you're dealing with. So rigorously, we call this as formula for S squared an unbiased estimator of the true population standard deviation. Look at us becoming so fancy. We will get to these once we do some more continuous math with probability distributions. Okay? And you can prove that you need n minus 1 in the denominator. Okay? So always trust the math. All right. So how do we do this in Python? Again, from NumPy, we call numpy.var for variance. So that gives us the variance. It's a squared measurement. The units, the dimensions are in the square of the variable. So you're doing the variance on salaries. The variance is going to be in dollars squared. You're doing the variance on temperature. It's going to be Kelvin squared. It's meaningless, but that's the variance. Next, we're going to take the square root, and then that brings us back to the real units. But in numpy.var, you have at a minimum two options. The data that you want to compute the variance for, just like we did earlier with the mean, but you have this additional parameter called DDOF. Now that allows you to determine whether you are doing a sample variance or a population variance. Okay? So it is literally, it means delta degrees of freedom. So they still use the word degrees of freedom. So whatever value you put in DDOF, the denominator in the S squared formula is n, the total number of points, minus what you put here. So therefore, if you're computing the variance of a population, your DDOF should be 0. If you're computing the variance of a sample, your DDOF should be 1. Okay? So now you go and reassess every time you are trying to compute the standard deviation in your budget, in whatever calculations you're making. Make sure whether you have, most likely you have a sample, so make sure you make that correction because it will change your results. Okay? So if we still have the data from last time, I still have the Jupyter notebook actually open. Let's just call in the numpy.var for the few data sets that we worked with. So I'm going to escape here and still have this over here. Okay? I hope you still have these with you. So let me turn without messing up this. All right. Okay. So I'm going to reload the uniform data, and we did the mean and the median last time. And I'm also going to compute the variance. Variance is equal mp.var. And I'm going to give it data. And if you press Shift-Tab, it gives you all the options. Now notice, it defaults to a population standard, a population variance. DDOF is equal to 0. But in this case, I only have a sample. I don't have the full population. So I'm going to put DDOF equal 1, delta degrees of freedom equal 1. So you will find the same option if you're using Google Sheets or Excel. So they call it DOF sometimes. So it's the same thing. It means the same thing. So next time you're computing a standard deviation or a variance, make sure you put the correct number of degrees of freedom. Okay? All right, and then we can print the variance. All right. Okay. And so over here it's giving me a variance of 0.08 whatever units squared I have in this distribution for salaries and whatnot. So there's hardly, the spread is not too high relative to the mean. The mean is at 0.5, and I have less than 0.1. So the spread of the data is not spread that far away from the mean. So on average, the data spread in squared units is 0.08. So once you take the square root, that's going to be a little higher. So remember, this is not a distance. It's the square of that distance from the mean. Okay? So to get the distance, you need to take the square root of that, which is the standard deviation, as we will see next. So I'm just going to copy this and go down here and do the same for these data. And again, the variance here is 0.98. So once you take the square root, that's also going to be around 1. That's the probability of this particular distribution. And so you do the same for all the data. It just gives you a number. What we do with that number is going to be important later. Finally, thank you so much, Sam. All right. Okay. So here's an example just for you if you want to do it by hand. Jasmine started driving for Uber. The number of rides she has given each day for a sample of 5 consecutive days is, on the first day, 3 rides, 2 rides on the second day, and so on. Find the variance for the number of rides. And so first, this is a sample, and they tell us for a sample of 5 consecutive days. So it's a sample mean. X bar is 4, and then the sample variance is this guy, formula over n minus 1. And you get 2.5 rides squared. Okay? I know it's like a weird measure, but it is what it is. Once we take the square root, it brings us back to dimensions of rides, which is what we will care about. Okay? So then the variance in her data would be about maybe 1.2 rides or something, right? So that's kind of how much of her data is. So again, if we continue with the variance and take the square root of the variance to bring the dimensions and the units to the original units of the data we have to take the square root of the variance, right? So it brings us from rides squared to ride, from dollars squared to dollars, to a true distance on the distribution. Now you can take the square root of you can compute the variance first and take the square root of it, or you can straight on go to numpy.std for standard deviation. And again, it takes data and DDOF. So same rules apply here. DDOF is delta degrees of freedom for a population standard deviation. This is 0 for a sample standard deviation. This is 1. So let's go back to the slides and to the Jupyter notebook and find the true distance here. I'm going to do stdev, so standard deviation, np.std of data, and then DDOF equal 1. And I'm going to run this again, and then print standard deviation. So I'm showing you bad habits here. I'm not explaining and putting comments and writing text because I don't have time to do that in class. But in your homework assignments, I'm a bad example here, okay? You make sure you write, you put comments, you explain what you're doing, okay? STDF. So now this tells me the standard deviation is 0.28. So about so about this much, like actually or more. So from the mean. So on average, so this is one standard deviation. And you can plot a vertical line to show one standard deviation away from the mean. Okay, so this would be on either side of the mean. On average, the data is about 0.28 units away from the mean. Okay, that's how you think of that. For this normal distribution, it's going to be close to 1 because the variance was almost 1, and the square root of that is 1. So stdev is equal mp.std data, and then ddof equal 1, and then print stdev. And yep, indeed, it was 0.99. So, what is 1 unit? So the average was about 2.5. So I think this is just about 1 unit, right? That's about 1 unit. Okay, that's on average where the data is spread. Now, over time, you will develop a more intuitive feeling of what one standard deviation means. And once we start working with normal distributions, we will learn some cool tips about the normal distribution, that about 68% of all data falls within one standard deviation, which is something you know. Right? We will be able to derive that later. But that's a rule of thumb we will learn a little later in these slides actually today. Again, there's another example here. Data contains from data for the ages in years of every patient seen by Dr. Dabbs at his urgent care clinic one afternoon. Calculate the standard deviation of the ages of his patients that afternoon, ages 11, 18, 25, etc., and consider this as a population. So, we're going to consider just the population of patients in that afternoon. And the key word here is every patient seen by Dr. Dabbs at his urgent care. And then you do the calculation, and then on average, the standard deviation was about 15 years. So on average, his patients differed by plus or minus 15 years of age from the mean value, okay, which was 35 years of age. Now, what is your interpretation of the standard deviation? I know many of you have used the standard deviation before, okay, in your undergraduate research, in your high school possibly. What is your interpretation? Go ahead.
The standard deviation, like you have said in the past, is basically most of the data is going to be one standard deviation close. Then if you add another standard deviation, even less of the data, then I think only 2% of the data, if it's a normal distribution, is outside of the second standard deviation.
Yeah, if it's a normal distribution. Now, thankfully, we will see that a lot of things tend to be normally distributed. But yeah, that's one good interpretation. It's a different interpretation. So who else? Yes, Alex.
You want like an R-squared value close to 1 for...
Pardon me?
You want an R-squared value or a standard deviation close to 1 for a fit to...
For a fit, so that's the standard error, right?
Okay.
So the standard error is the equivalent of the standard deviation. So that's a great point, because that's how I explain regression. So the standard error, so what Alexa is saying is that when you are doing a data fit, okay, you do a regression line along a bunch of data, and then that line is not going to go through each and every data point. It's going to pass through the middle, and those data are going to be spread around that line. That spread, the measure of that spread, is called the standard error, but it's the equivalent of the standard deviation. Actually, it's the equivalent of the standard deviation. So, but it quantifies the error in using a regression line to model the data, right? Okay. Okay, what else? Yes?
How far on average the data is
from the mean, correct? Yep. What's your name? Okay. All right, who else? Okay. All valid interpretations. This is, different disciplines will interpret this differently. I'll give you 3 interpretations I like to use. The typical distance from the average, that's what most of you said. The second interpretation is the noise level in the system. So when you see a signal and it's like very noisy, and you immediately ask, okay, what is the mean, right? With my radon data, what was the mean? Like 2.4. But then that noise around the data, up and down, the average of that distance of the noise is going to be the standard deviation. The larger the standard deviation from the mean, then I have more noise in my data, possibly, right? Because I have more points scattered around the mean value. Now, this one is the one I like. I like to think of the standard deviation as actually an error, okay? If the things were ideal and everything was perfect, all data will line up along the mean. All of the data will line up along the mean, okay? And therefore, if you use the mean to explain any data set, your standard deviation is the error committed in using the mean to explain those data. So if I tell you Dr. Dabbs's urgent care practice, he treats patients who are 35 years of age. The error committed by making that statement is 15 years because that was the standard deviation. Okay? So if you want more about that, you can look up my lectures on regression, where I motivate the study of why we do regression. But I like to think of the standard deviation as the error committed in using the mean to represent all the data, however scattered it is. Okay, now I'm going to ask you another question now that you are standard deviation experts. Which of the following data has more variability? So measure that with variance or standard deviation, doesn't matter. Okay. I have a bunch of salaries with a standard deviation of $50 and a bunch of salaries with a standard deviation of $500. Both are the same units. Which data set has more variability, more spread? Okay. Oh, wow. Okay. Let's all of us answer. Okay. The $500. Why?
That's like the range of
Larger, much larger distance.
The 500.
Are the salaries the same data set? Like, is that the same population?
Why?
Because there could be like $1 million, and then the variance or the standard deviation is 500.
I don't know about your answer, sir. Yeah. Okay.
We need to norm it.
Okay. So I'm gonna come back to you. What do you think?
I would say 500 because regardless, I mean, the more variability is 500 because regardless of how spread out your data is, if you have a lower expected error and it's more spread out, or even if it's less spread out.
Mm-hmm. Okay. Yeah, because 500 is a larger number. They're the same units. Who else had their hands raised? Come on. The front row is winning, guys. Come on. Yes.
It depends on like what you're working with. Like if everyone is all making $50 and the same, like they can be equal.
So similar to Benjamin's answer. Okay. Sorry, Benjamin. I read.
You can call me Benji, yeah.
Sorry, Benjamin. Who else? Okay. So, do the rest of you like have no opinion, or you want to take a vote? I mean, this is not a democracy. There's one right answer, but do you want to take a vote? Yes. Yeah. Who stands with Benjamin and Savannah, and who stands with? Okay. It's not very many. Okay. What about the rest of you? Are you with Sam, Alex, and Rachel? Huh? Okay. All right. I will put my wager on Benjamin and Savannah. Because remember, the standard deviation is measured with respect to what? To the mean. If we don't know what the mean is, this question is meaningless. Because like Benjamin said, what if they're making $1 million and the spread is 500? That's nothing relative to the million. What if the $50, they're all making $60 on average? Then $50 is a huge difference. Remember, the standard deviation is measured relative to the average, and that's what I stressed out at the beginning. It's always measured relative to the average. So,
But isn't the variance Darn it. Okay. I see what you did there.
Yeah.
Variability instead of variance.
Yep, the variability, like how much is the data spread. So to really compare these two, we need to understand, to know what the mean is, what the mean value is, and somehow rescale the data, because these data are going to be at two different scales possibly. If the second set of salaries, the average is $1 million and the spread is 500, how can I compare that to data at a mean of $60 and $50 spread? They're the same units, but they are at vastly different scales. So we need to rescale the problem so that we can compare. And the way we scale this is through something called the coefficient of variation. And that simply takes, if you're trying to compare two distributions, okay, of the same thing, they're measuring the same thing, but they have different means, different standard deviations or variances. What you do, you take the ratio of the standard deviation with respect to the mean value. So that normalizes everything. It tells you how far away are you from the mean with respect to the scale of the mean. So then $500 over $1 million, okay, is going to be insignificant compared to $50 over $60, right? So then there's going to be less variability in that case, although 500 is bigger than 50. It's a matter of relative scale, okay? It's a matter of relative scale. So that's called the coefficient of variation. So let's take this example again. Salaries with standard deviation of $50 and a mean of 60 has much more relative variability than salaries with a standard deviation of 500 and a mean of $2,000, right? The variability here from this calculation is 83%, and here for the second set of salaries is only 25%. So if you were to normalize these graphs and kind of plot them on the same scale, one of them is going to be wider than the other, okay? So we have to bring them back to a relative measure, okay? So the same way when we did error analysis in numerical methods. A 1 meter error on in a 10 meter measurement, okay, is a 1 meter error on a 10 meter length table is not the same as a 1 meter error in a 100 kilometer bridge. Because the 100 kilometers is 100,000 meters, and your 1 meter error is nothing compared to the 1 meter error on a 10 meter table, which is 10% of the table. Okay? So that's the same idea here. Okay, that's how you can compare two distributions. All right. Next is the empirical rule for bell-shaped distributions, which, who knows about this rule? 68% of the data. Okay, in what context? I'm curious. In what context did you learn it?
Business, information systems class.
Okay. Others? Yeah?
I want to say I learned it in either a math class or a physics class we were talking
About normal and standard deviation, yeah? Yeah?
I think like maybe
Calculus, okay. Talking about distribution. Who else? Yeah?
That's class with school.
Okay. Very nice. Okay. So the normal distribution is going to be a fundamental part of our inferential statistics later. There's like this really beautiful theorem that I told you we will demonstrate together in class by running big statistical experiments and understanding. Everything tends to become a normal distribution, and so that's why we study it so well. Okay, for data that's distributed like this, like a bell curve or approximately like this, you can immediately make quick inferences about the data and say that about 68% of the data lies within plus or minus 1 standard deviation of the mean. Again, everything is relative to the mean. So if you take the mean value, you go 1 standard deviation out, there's about 34% of the data is here. And if you go to the left side, there's another 34% of the data there. Now, why is that important? You can draw statistics by, if somebody tells you, well, the average weight of kids, born in Utah is like 1 pound with a standard deviation of ½ pound, then you could say 68% of the babies born in Utah are going to be, plus 1 pound plus or minus 0.2, right? And that's kind of how you use this. Then, if you go 2 standard deviations out, then almost 96% of the data is contained there. So most of the data is going to be within 2 standard deviations, right? And then this gives you the breakdown in each bin. So 35%, 34% here, about 13.5% here, and about 2% out there on either side. Yeah. And that's a summary of what I just said. And finally, the next thing is just to do the standard deviation or variance for group data, which we did for the mean value. When you only have the frequency distribution, you have the counts, and you do not have the full, you only have the bins and the counts in the bins. You know, last time we took the midpoint to compute the average and multiplied that by the count, so that ended up being a weighted average. In this case, you do something similar, but the formula changes a little bit, so you still have xi minus x bar, or xi minus mu. So this is a typo here. Let me fix that right now. Okay. So for the population or for the sample, but instead of xi, you're taking the bin midpoint, x bar bin I. So that's the average of the bin or the midpoint for bin I. And you also need to multiply by the count. How many counts were in that bin? Now this summation doesn't go over the number of points. You no longer have a number of points. You have bins. So you go over the number of bins. And notice what I put here, I going from 1 to k, where k is the number of classes or bins. Okay, this explains all of it. There's an example after this. I'm not too worried about this calculation. It's fairly just the same formula we did with the mean values. Last time you can do the same in Python. Take the midpoints, you do the slicing, right? And we already did that. It's just a different calculation. There's an example here from the textbook of 3.2.8 that does that, and you can go through it. I'm not too worried about it. So that's the standard deviation. Let me check here. And there's a few more examples in the textbook as well. Okay. So a couple of minutes and I'll give you a break. Actually, yeah, let's do this and then we'll take a break. Okay? Finally, measures of relative position. So those are all descriptive statistics, like what can you tell me about the data? The relative measures of relative position are going to simply tell us how many people are in the first 25% of the data, or the last 90%, the 90% of the data, what does it contain? Just questions like that, right? So how many people are, or a given value, what percentile is that? So, when I take my kids to the pediatrics clinic, they measure their weight, their height, etc. And then they give you this percentile graph. Your child is 50th percentile in height, or 60th percentile, in weight and whatnot. So what does that mean? That's what these measures of relative position are going to tell you. So we define the percentile. We say the pth percentile, so the 25th percentile or the 50th percentile is the location of the data point where p% of the data is less than p. So many p's. So 25th percentile is where 25% of the data is less than that value. Okay, and 100 minus p% of the data is above that. Okay. So 2 examples here, like for example, the 10th percentile of the data is the value where 10% of observations are below it and 90% are above it. So it's a location on the x-axis in a histogram or a distribution, frequency distribution. The same way we drew the median, that was the value where half the data were below it and half the data were above it. This just generalizes that concept. We're no longer thinking about 50%. You can think about 25, 30, 60%, whatever you like. Okay? And these are great ways to spin statistics, because you can keep looking for a value that fits your narrative and say, oh yeah, did you know that 65% of people who smoke do not necessarily get cancer or something, because if you're like selling cigarettes or what. I'm making this up, okay? You shouldn't smoke. I used to smoke, but I quit 15 years ago, so. Okay, now how do you access this with Python? Again, from good old NumPy, and you call quantile. Okay, you call quantile. You give it the data, and the quantile of interest is the fraction. So that number Q is not 25%, it's 0.25. Well, it is 25 over 100, right? But you give it as a fraction. The quantile is a value between 0 and 1. This Q value is between 0 and 1. Okay, so you give it value 0.2, is going to give you the 20th percentile, or 20% of the data are below and 80% are above that. Okay, so we can use this on our data here. So let's pick this guy. Let's pick this guy. All right, and I'm going to do, which one do you want? Which 20th percentile? Okay, so P20 is mp.quantile, and I'm going to give it data, and I'm going to say Q equals 0.2. Okay, and then print P20. Okay, and then PLT, I'm going to also draw that line, vertical line, X vertical line, P20, and I'm going to make it green. Let's put some more bins here, shall we? Bins equal 30. All right. Oh, horrible green. Let's put yellow. Okay. So that's this value of 1.5 is the 20th percentile. So 20% of the data are below 1.5 and 80% of the data are above it. Do you have a question?
Oh, sorry.
Yeah. Time for a break, I guess, to stretch. Yeah. So, fairly straightforward. But it's a great way of computing quantiles, because doing it by hand is annoying. So just using Python. In Google Sheets, you can use the same. I think it's called quartiles. In Excel, I don't know what it's called. But there's an equivalent. If you know what you're looking for, how do I compute quartiles or quantiles or percentiles in Google Sheets or Excel, you'll find the answer. Okay, one last question before you take a break. What is the 0th percentile or the 0th quartile? What is the 4th quartile?
The 0th quartile, would that be like bottom 2%, and the 4th quartile would be like the top 2%?
Why 2%? So quartile is one, so the quartiles are the quarters, right? So the first quartile is 25%, the second quartile is 50%, the third quartile is 75%, the fourth quartile is 100%. So that's the maximum value, right? What about the 0th quartile or the 0th percentile? It's not the 2%, it's the minimum value, yeah, the bottom. Not even 2%. So the 2% would be the 2 percentile, right? Yeah. Let's resume. Last piece of descriptive statistics. So I couldn't cover this when we were doing graphical description of data, because I needed to do some numerical description and specifically get to the quantiles. So it turns out if you combine the median and the first, second, third, and 0th and 4th quartiles together, you can describe a lot about the data. You can tell where the middle is, where the 25% of the data is, 75%, min and max. And on top of that, you can add a few other things. So people came up with a really great way to display these. And again, if we take Q0, Q1, Q2, Q3, Q4, so that's the minimum, 25%, median, 75%, and 100%. And together, they form 5 numbers. We can put them in what's called a box plot. It's simply a visual representation of this five number summary. This is what a box plot looks like. It summarizes an entire distribution. Could be 1 million data points or 5 data points or 10 data points. One box plot summary summarizes the entire distribution. It's got a bunch of vertical lines, whiskers, and in the middle it has a box, and there's a line also in the middle. And what those mean are they correspond to the quartiles, exactly 25% each. So Q0 is the minimum, Q1 is the 25th percentile, Q2 is the 50th percentile, but it's also 25% away from Q1, so that distance is to scale, right? So you see kind of the median is closer to that right-hand side of that blue box. And then Q3 is the 75th percentile. So from Q0 to Q3, there's 75%. Between Q1 and Q3, there's about 50% of, there is 50% of the data. From Q2 to Q0, there's 50% of the data, and so on. And then, and remember, these are values, all right? So it could be in dollars, $60, and then, $100, and so on. And then all the way to Q4, which is the maximum of the data. That's the simplest box plot you could create. You could see it horizontally. I've only seen it horizontally when I'm looking at one single data set. To summarize the whole thing, I get a nice, beautiful, big box plot summarizing the entire data. It doesn't tell you how the distribution looks like or standard deviation, whether it's normal, it's skewed or not. It doesn't tell you that information, but it gives you a lot of other information that is useful. Sometimes you see the box plot plotted vertically, and especially when you're summarizing over time. So you could be measuring temperature, for example, on a daily basis. Okay, you're measuring temperature on a daily basis, and you want to compare how the temperature is changing from week to week. So each week you have a distribution of temperatures, agreed? But then from each week you have a distribution of temperatures. You can plot all of the data together, or you can take the first week and make a box plot of that, and then take the second week, makes a box plot of that, and so on and so forth, and then compare the box plots instead of comparing the full distributions per week. Why would you need to compare per week? Because it makes sense. Like if you're comparing Earth, we'll do an example, Earth's surface temperature on the Earth, you're going to compare over each year, right, or over each decade. And you have a distribution of data per decade, right? You want to track how is this changing from year to year. Oftentimes, Q0 and Q4 are way too small or too large to include. So people replace Q0, instead of taking the min, they take the 2%, for example, or they take the 5th percentile. And the Q4, instead of taking the hundredths or the maximum, they take the 95th percentile or the 90th percentile. And oftentimes when that's the case, not oftentimes, almost always, it is indicated in a legend. Like they will tell you, oh, the top whisker is the 95th or the 80th percentile, whatever they choose. Okay? Now, sometimes you can also see the mean value plotted on that box plot. Because the closer the mean is to the median, so the closer Q2 is to that yellow dot, then we know the distribution is symmetric. If it's to either way, you can determine if it's skewed to the right or skewed to the left, right? And then finally, this difference between Q3 and Q1 can help us determine outliers. So how do you tell if a value is an outlier or not? You kind of visually spot it. It's way out there. But a convention that people have accepted is that if any data point is above Q1 plus 1.5 interquartile range, which is Q3 minus Q1, so that distance, then that's an outlier, okay? And any data above that, above Q3 plus 1.5 IQR, and any data below Q1 minus 1.5 IQR, it's an outlier. And oftentimes what you will see those data points show up as circles outside of this whisker. Because if you choose this whisker to be 5% of the data, then, or even the 5% of the data, then that outlier is going to almost always be below or above that top value. Yes?
Can you have Q0 and Q4 if you have outliers?
Yeah, no. So Q0 and Q4 will cover. So you will not see the outliers there, but Q4 will be very, very high. So Python by default uses this formula, okay, for Q0 and Q4. So Q0 in Python is exactly this guy. It's Q1 minus 1.5 IQR. And in Python, Q4 is exactly Q3 plus 1.5 IQR. It's not the maximum. Okay? So then if there's values above that, you're going to see them as dots. We'll do an example together. Now, in NumPy, this is simply called plt.boxplot, and you give it the data. And it does things with the data. Now, we have to talk about that data. I cannot give it the data that I gave it that we worked with earlier, because that data we worked with earlier is just one array of data. What it's going to do is just going to generate one box plot for me. Okay, one box plot for me. If I want to look at box plot as they change over time, or as they change over some variable that's changing, I have to provide an array of arrays. Okay, and then you have two options here, and we'll work through all of these examples together. If a two-dimensional array is provided, then the box plot is going to take, so an array is going to have rows and columns. Think of it like a matrix. What box plot will do, it will take the first column and do a box plot for the first column, take the next column, do a box plot for the next column, and so on. Okay, not per row. If you wanted to do it per row because your data happens to be like that, you have to transpose it. The other option, if you provide a sequence of a list of one-dimensional arrays. It's not a 2D array, it's an array of arrays, a list of 1D arrays. Then it will go through each array, makes a box plot for each array, and then plot them next to each other. So let's do some examples together. Okay, let's do some examples together. And let me create a, hold on. I'm going to create a new notebook. So you go ahead and create a new notebook, please. And oops, go away. Okay. There you go. So in class, box plots. Okay. So again, this is located at the same directory of these guys. So I'm going to go and, let's say, just import. Let's take the boilerplate here, copy paste. All right. And then I'm going to take these data here and just do a box plot on them. Okay. So put your Jupyter Notebook next to your other Jupyter Notebooks, next to the data we were working with. My recommendation is for each chapter we're doing, create a directory called in-class Python stuff and just dump everything in there. Next chapter, make a new directory, dump everything in there, and just work in that working directory. All right, so I'm going to load this data, and I'm going to do plt.box plot and data. If I do this, this should give me a single box plot. Although the data had 10,000 entries in it, from box plot it saw one array, okay, and it's just going to do one box plot for the entire data. Now notice here, these guys are the outliers. Okay, these guys are the outliers. These little circles, they are outliers. Now, how do I verify this? If I go on box plot, I press Shift Tab. Wow, there's so many options, but I'll scroll down a little bit. See now, by default, Python, the smallest whisker is Q1 minus 1.5 IQR, and the highest whisker is Q3 plus 1.5 IQR. and everything else, they call it flyer or outlier. You can change that. So if you scroll down to the, what is it, the method for the whiskers, yep. So you can change the method. Hold on, you change it. There's so many options here. I like the default position that they use. Okay. Yeah. So whiskers, you provide float or two numbers here to determine what's multiplying the interquartile range. Okay, so if a float, the lower whisker, it's just explained. So you can change that by changing this argument. Okay, you can change that by changing this argument to put min and max. I don't recommend it because sometimes the max is so high, then it's going to screw up your entire plot. It's going to look really bad. Okay, keep it as it is. It's a good standard. People accept this method. Yeah, so that's it for the entire. Now we can customize this. If we have time, we'll work on this in a little bit for customization. But I want to go, and now I'm more interested in plotting a sequence of box plots. Okay, so what I'm interested in is looking at how the data layout is going to allow me to do box plots, a sequence of box plots. And we said we have two options. I want this to go away. Why doesn't it leave me alone? Okay. Option 1 for box plot, option 2. Option 1 for box plots, list of arrays or array sequence or array of arrays. So let's say I have my data as, okay, I'm going to do just like a few data points, 1, 2, 4, 5. That's horrible. My passwords are terrible if I were to create it, like 1, 2, 3, 4, 5, right? 2.1, and then we put 8, let's say here. That's my first distribution. Let's say these are temperatures or money you bribe your kids with or something. Okay, and then 2, 3, 1, come on. Every parent does that. Okay, 3. Okay, so how many data points I have here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I want to show you that the advantage of this method is you can have unequal sizes of your arrays. Okay, so you can have more measurements in one array than 3.4. Okay. Now when I do the box plot here, plt.boxplot of data, it's going to create 2 box plots for me. Let me clean this up here for a second. Okay, it's going to create 2 box plots. The first one corresponds to the first array in the list. The second one corresponds to the second array. Now, it automatically, by default, picks tick marks to say this is array 1, array 2, but later we'll customize those. This could be week 1, week 2, week 3, and so on. So that's method 1 of providing data. The advantage of this method is that these arrays do not have to be equal. Okay, these arrays do not have to be equal. Okay? This is not a 2-dimensional array. It's an array of arrays. Okay, a 2-dimensional array, you access it with 2 indices in the arguments. This one you can't. It has to be one index and then another index. Okay, so you can't say data 0, 1 is going to crash. Okay, to access data 0, 1, you have to go data 0 and then 1, and then that gives you the value. So it's an array of arrays. Okay, option 2. Option 2, 2D array. Data, I'm going to create an empty 2D array, np.zeros, and I'm going to do it 3 by 3. Or 2 rows and 3 columns. Okay, so that gives me. So if you do data.shape, it's going to give you. That it's a 2. Let's do it 2 by 5. Okay, so we have 5 entries. So data 0 now. Okay, so data 0 and everything is going to contain, we can fill in 5 entries in this one. So it's going to be a numpy.array of 5 values. So I'm taking the first, so this is 2 rows and 5 columns. So I'm taking the first, no, I need to invert this, do this the other way around, sorry. Okay. So I need to do this as 5 rows and 2 columns, okay? So data 0 gives me, the first index gives me, is going to give me, no, sorry, this is going to give me the first row. My bad. I'm confusing my indexing. My apologies. 2 and 5. So data 0 is going to give me the first row, and then I'm going to fill it out with 5 values, 1, 3, 5, and then 2, and then 1, 2, 3, 4, 5, right? Should work. And then the second data point is on the second row, which is the first index is 1. That's the second row, and I have 5 values. And then what this will do is let's vary this a little bit, 2.1, and then 2.9, 2.0, and then 5 here, okay? Now, PLT, what do you think is going to happen now? PLT.boxplot. How many box plots am I going to have? 2 or 5? 5. 2. Okay. So remember, in a 2D array, it's going to average per column, not per row. But I have 2 rows here and 5 columns. So it's going to take the data, it's going to take these and make a box plot, these and makes a box plot, these, and this. So it should give me 5 box plots, which is box plots. Box plot is going to give me 5 box plots, which is not what I want, right? So what I can do is simply transpose the array. You put dot t, transpose, and now you're doing it correctly. Now this first box plot corresponds to this first array. The second box plot corresponds to the second one. The disadvantage of this method is that all data have to be of the same size. So if 1 week you sampled 15 more data points, you have to make sure that your array created has at least enough room to fit those. Although in week 1 you only had 5 data points, so you're going to have zeros everywhere else, but that could screw up your statistics, right? So, then if you have unequal data, make a list of arrays. It's cleaner and easier. Okay, so I have a problem that we can work through together. And okay, so Canvas is broken. I want you to download the data at this short URL, and it's data for global surface temperatures for the last 7 decades. Okay, for the last 70 years, and you can download it from this URL. It's just simply a text file. Just flat, all the data. There's 70 years worth of data. You got it? Okay. You guys good? Put it next to your Jupyter notebook, please, okay? Okay. So now let me make sure I actually have it in here. All right. So global surface temps or data. Oh, let's just call it data. Data is equal mp.load txt. Again, I'm doing this in the simplest way. Global surface temp per decade. And just load that up. Now, first thing you want to do is flirt with the data. Just like either plot it or just kind of see the shape. You can print it. Just a bunch of numbers, bunch of temperatures, data.shape. If I type that, oh, okay, I got 120. I got 7 rows and 120 columns. So that's 120 temperatures for each decade, right? Why is that? A decade is 10 years. Each year is 12 months. I have 1 temperature per month. Over 10 years, it's 120 temperatures. So I'm taking the daily average and then taking the weekly average, taking the monthly average, and storing that over the an entire year. That's 1 decade. That's 1 year, 12 temperatures. Okay, over a decade, 10 years, it's 120 temperatures. So I have decade 1 is 120 temperatures, decade 2 another 120, and so on. So I need to plot this. But I need to plot this smartly. So if I were to go and just do plt.box, naively plt.box plot data, I'm just going to get junk. Okay? That's not what I want, because this is plotting 120 box plots. It's a horrible, bad idea. And that's wrong. That's not what I wanted. I want to plot per decade. But my data, remember, this is actually a 2D array. That's why we did the example earlier. So this is going to plot per column. Okay, so it's going to take the first row, okay, and then we're going to plot 120 values. Okay, that's not what I want. I want to transpose that. Okay, so if I transpose it, then I get something more meaningful. Okay, I get something more meaningful. First decade, whatever we started, second decade, third, etc. You see that, they're slowly climbing. The median is also very slowly climbing, right? So we started, let's say, whatever, at 17.5, and we're up closer to 18 in terms of the median. How can we show the mean value? Well, boxplot has all of that for us. If you shift tab here, you got a bunch of other things, other options here, but then you look here, there's an option called show means. Okay, so I can turn that on. I can put show means equal true. And then that will show the mean value for me. All right? And then look at that, beautiful. Mean value was starting at around 17, and then it's climbing up slowly to 18. Okay, over the last 70 years, right? So you can see the trend, you can determine the trend, you can look at how the data is distributed. I don't have any outliers in the data, I don't see any outliers. You can hide the outliers, but now you can adjust this plot to make it cute and more pretty than it is, okay? And you can add annotations here, etc. If I have time, I need to finish 3 more slides. And if I finish them early, I'll come back here and I show you how I would beautify this. Gonna add some more labels here, like year 1, decade 1, etc. And then add some color to the box. But you get here, this is great. There's so many options to make this nice and clean. You can hop and Google this or ChatGPT or read the documentation. I would put color over here. Okay, I would draw a line connecting the mean values to show kind of how the means are connected, right? And then I would add tick labels over here. I would put, temperature on Celsius over here. So this is Celsius, not Fahrenheit. Okay, it would be really bad if it's Fahrenheit. Okay, so 16 Celsius is 61 Fahrenheit. Okay, that's my anchor point. I still cannot think in Fahrenheit because I grew up in Celsius. I'm like, oh, temperature is 80. I'm like, oh my God, we're all gonna die. No, it's 80 Fahrenheit, right? But then the anchor point and the calculation is horrible. It's like you need to multiply and divide and whatever. So I was like, 61 is 16 Celsius is 61 Fahrenheit. But the worst part is Fahrenheit is not linear. It's not like you add 2 more degrees, you're gonna twice as hotter, or like even Celsius is not linear. But anyway, I still struggle with Fahrenheit. Okay. Okay.
Think about the 100 degrees is the hottest day you've ever experienced. And
I suppose.
0 degrees is
Yeah.
the coldest day you've ever experienced.
But the problem with these scales, okay, you asked for it. So the problem with the Celsius and the Fahrenheit scales is that they do not have a true 0. That's why you use the Kelvin in science, the Kelvin scale. Something that's 20 degrees Celsius or Fahrenheit compared to something at 10 degrees doesn't mean it's twice as hot. unless the temperature was in Kelvin, because Kelvin has a true zero. Okay, really, the absolute zero is where there's no motion at all. So something at 300 Kelvin versus something at 600 Kelvin, that's twice as hot. But something at 600 Celsius is not twice as hot as, yeah. Pardon me? Oh my goodness, Rankine. Oh. I haven't heard of that temperature in a decade. Okay, we do one last thing before I let you go, because this will be on your homework. So another way to compare, so we talked about comparing variability between distributions, and that was in the sense for the entire total distribution. Okay, standard variance or standard deviation of distribution A versus distribution B. But what if you had a situation where one subject in a class or in a population, one subject had a measurement, had a value, like they earned $80,000 at their company, and then the other person earned $70,000 at the other company. Are they making relatively more or less? Or like, how do they compare? How can you compare the two? Okay, so this standard or z-score value allows you to compare that. This is going to be critical in inferential statistics, so we just introduce it now. Here's the example. Jody scored an 87 on her calculus test and was bragging to her best friend about how well she had done. She said that her class had a mean of 80 with a standard deviation of 5. So, 80 and 5, we can do a coefficient of variation, but that only measures variability. Okay, but we can't tell if Jody did better than her friend. Her best friend Ashley was disappointed. She had scored only an 82 on her calculus test, and the mean for Ashley's class was 73 with a standard deviation of 6. Which one of them did better? How do you compare? We can compare the variability between both distributions by dividing the sigma, the standard deviation, divided by the mean, but that doesn't tell us if Jody did better than Ashley or vice versa. What you need to measure in this case is called the z-value or the standard score. You take the individual value that you're looking at, which in this case is the grade, 85 versus 83. That's your x value, minus the mean, whether you're a sample or a population. If it's a population, it's mu. If it's a sample, it's x bar. And you divide by the standard deviation. In your homework, you will understand what this does to a set of data. So I'm not gonna tell you, but all I can tell you is that it allows you to truly compare these two values from the different classrooms. Okay, it does something to the data, something really unique, but it rescales it in a way that you can compare the two. So then, if you do this calculation for Jody, she gets a z-score of 1.4. But for Ashley, she gets a z-score of 1.5. So actually, if all things are being equal, Ashley did better than Jody. In other words, if Ashley was in Jody's class, she would have scored a higher score, right? She would have scored a higher score if the same conditions were met. This is what the z-score does. We're going to be using it throughout inferential statistics. In your homework, I will ask you mathematically to prove, guide you through a series of questions, and you'll understand why this works, why we can compare Jody's class to Ashley's class without even, batting an eye. Like, oh, yeah, this is going to make sense. And the way to phrase it is that if Jody was in Ashley's class, she would do a little worse than Ashley, and if Ashley was in Jody's class, she would do a little better than Jody. All right, thank you so much. Have a good weekend. Godspeed. I'll release the homework in a little bit. Okay? I will see you next week.